Would like to compare three similar organic compounds shown right here. You can clearly see for ethane, the angle is 109.5, while in ethylene it's 120 degrees, and for acetylene it's 180 degrees. We can explain the origin of these angles by applying the same principles we applied for mononuclear molecules. You look at each one of the carbon atoms as a central atom, and you apply the same rules to predict the angle and explain the formation of the multiple bond. So in this regard, the multiple bond will form based on the type of overlaps that will occur between the hybrid orbitals. So if you have head-to-head overlap, that's going to be called a sigma bond. The electron cloud is going to be localized in between the two bound atoms. But if you have a side-by-side overlap, the bonding electron cloud in this case is going to be localized on top and below the two bound atoms, and the bond formed in this case is going to be called a pi bond. If you have s orbitals, you will only have one orientation for the overlap, which is going to be always head-to-head overlap. So it's going to always result in a sigma bond. If you have an s orbital overlapping with the p orbital, is going to be always a head-to-head type of overlap, forming a sigma bond. But if you have two p orbitals, we will have two possibilities. We'll have the possibility of having head-to-head type of overlap between them that will result in a sigma bond with the electron cloud localized in between the two bound atoms. And we will also have a second possibility where the two p orbitals will overlap side by side. And in this case, the bond formed is going to be called a pi bond. Again, the electron cloud in this case is going to be localized on top and below the two bound atoms in the molecule. If you look at each one of these carbon atoms, you will clearly see that each one of them has 4 domains around it, which means it has an sp3 hybridization with a tetrahedral electronic geometry with a 109 angle between each two of them. And the possible overlap in this case is going to be a sigma overlap between an sp3 hybrid from this carbon atom with an sp3 hybrid from the second carbon atom. And the other 3 sp3 hybrids will make sigma bonds with the hydrogen atoms in this case. And that explains the shape of the molecule and the angles that we observe in this molecule in this case. But if you look at the ethylene molecule, you will find that each carbon atom is actually having only 3 domains, which means it's going to have sp2 hybrids that will be oriented in a trigonal planar orientation with 120 degrees angle between each two of them, while the unhybridized p orbital is going to be in a perpendicular orientation with respect to the hybrid orbitals. Hybrid orbitals will get involved in sigma bonding with the hydrogen atoms and one sigma bond with the second carbon atom. And that explains the 120 degrees angle between them and the side-by-side overlap between the unhybridized p orbitals, making a pi bond. And since these two unhybridized p orbitals are perpendicular to the plane of the hybrid orbitals, they will actually make the molecule rigid and will not allow rotation around the double bond, because if you try to rotate the molecule around the double bond, you will basically make the two p orbitals not parallel with each other, so it's gonna break the bond. So it's not possible to have this type of orientation, because in this case you will have one p orbital in this direction and the second p orbital in this direction, and they are clearly not parallel to each other. In this case, they will not have a bond in this case. And the fact that the pi bond prevents rotation around the carbon-carbon bond in ethylene causes the possibility of having two isomers of the same molecule, two molecules with the same composition, but with two different orientations of the substituents. So if you have two chlorine atoms instead of hydrogen on ethylene, the position of each one of these chlorine atoms is gonna have two possibilities. Either they will become on the same side in what is called a cis isomer of the molecule, or they will occupy an opposite sides on the molecule in what is called a trans isomer of the molecule. If you count the number of domains in case of acetylene, you'll clearly see that each of these carbon atoms has only two domains, which means it actually has sp hybrids that will have 180 degrees angle between each other, and that will leave two perpendicular unhybridized p orbitals on each of the carbon atoms. The sp hybrids will get involved in sigma bonding between the carbon atoms and between the carbon and hydrogen atoms, which will cause the whole molecule to be linear. And the unhybridized p orbitals will have side-by-side overlap with each other, which will make two pi bonds in the molecule that in total will make the bond between the carbon atoms a total of 3. One sigma bond between the sp hybrids and each other, and two pi bonds between the unhybridized p orbitals and each other.